Okay, hello everyone. Uh, I hope you can listen me clearly. If not, please let me know. Please confirm by sending a message that you can listen. Okay, thank you. And I'm assuming also that you are able to see the screen. Uh, yeah, thank you for confirmation. Okay, so. Last time we were talking about the internal architecture of our AVR microcontroller, and we had seen that it consisted of multiple components. For example, CPU, memory chip. Sorry, not memory chip. The memory itself, because it is on the same chip. It is not on the separate chip, and I/O devices. And then we also saw that within the ALU uh, you have different components like for example within the processor you have different components like instruction decoder, program counter register, general purpose register, and your ALU. So these are just some examples, right? Remember, this course is not about computer architecture. It is about using a microcontroller which is already designed for us, and we are basically focused on understanding the internal of that architecture, that microcontroller, and program it using the assembly language. Okay, so we said that our microcontroller has 32 general purpose registers, and other than that we have also special function registers, 64 special function registers, and then in the data address range we also have the static memory, right? So previously we said that general purpose registers, there you can use them as a programmer to hold any temporary value. That is not completely true. You can, but then there are some conventions which we need to follow so that the code is readable and understandable for all the programmers. So what are those conventions? So first thing is that let's first talk about R0. So R0 is freely available. Freely available mean that you can use it to hold any temporary value, like other many other general purpose registers. R1. So again, let me select the pointer. R1. So we use normally it always to hold zero, and we must clear it after usage. So for example, if you are putting something else in R1 other than zero, so once you are done, it's always a convention to put zero back into this register R1. It becomes convenient because, for example, if you are using all the time, you are sure that R1 is not holding anything else. You will always hold zero in your R1 register. Then in your program, for example, if you want to check some condition or you want to compare some other register with a zero value, you can directly say, okay, compare with R1. So it is like, a convenient source of zero value for you in the program. Other than that, your R2 to R17 register, when you are, so they must be saved and restored by the caller. What does it mean? Um Let me explain by going to OneNote. So first you need to understand what we mean by caller and callee. So I'm assuming here that you have experience with at least one high level language like C, C++, or Java, or Python, right? So in those languages, when you just okay. So in those languages, when you make a function call, so let's say you have a main program in your C. Let's say I'm assuming C language, okay, and you have a main method, not main program, main method in your C, and then this method somewhere down the line it calls another method. Let's say I'm calling it foo. So let's say you have some instructions, and then you say you invoke foo, but you make a function call, right? So now your main is your caller and foo function is callee, right? Now, when you are writing, not only in the case when you are writing your programs in assembly, but also in the case when you are writing your program in higher level languages, the data which is accessed by your for example, ALU is stored in registers, right? So we need to be make sure that uh, our Kali function, it doesn't overwrite some registers which are already in use by the caller function. So let's say now I'm moving to, I'm going to talk about in terms of assembly language. Now let's say that my caller function, it was using some registers like R1 and R2, okay? And then it makes a function call. Let's say it says foo. I'm not writing the complete program definitely. So it was using R1 and R2, and then it makes a function call foo, and once it comes back after the function call, it wants to use the values in R1 and R2 again. For example, let's say it says add R1 and R2 and put the result back in R1, right? But before doing this, our our foo function is called, right? So this function is first executed, right? So if this function actually overrides the values of R1 and R2 within the body of this function, let's say here the R1 was 1 and R2 was 2. So here I would expect that I will get 3. But if in the body of the Kali function or the foo function, if the value of these registers is overwritten, let's say R1 is set to 0 and R2 is set to 10. So, and then once function completes and we go back to the main function, so the result I will see will be 10, not 3, which will be incorrect, right? This is not what I would be expecting, right? So what we need to do is that, now let me go back to the slides. So what we need to do is that these registers R2 and R17 must be saved and restored by the caller, which means that it is the responsibility of the caller function that if it is using any of these registers R2 and R17 in its code before calling the Kali, or for example in our case the foo function, it is its responsibility to store them in memory and then make the function call, because we cannot take the risk, we cannot like we are not putting the responsibility on the Kali function or the foo function to not override these register. Maybe it will override, maybe it will not, we don't know, right? So it is the job of the caller that if the caller is using any of these registers R2 to R17 to hold some temporary some values which it want to use in future after making the function call, so it's its responsibility to store their values in the memory, and then when the control comes back from the function call, to restore their values from the memory. Again, let me again go back to the example. So here, this actually means that, for example, we are saying R2 to R18. So here we are using R2, right? So it will be the job of the caller to first put the value of this R2 register in memory and then call the function, make the function call foo here, this at this point. And once it returns back, before like executing the next instruction, the value should be loaded again back into the R2 register. So let's say here I am just drawing the figure for R2. So previously it was like written into the memory before making the system call, not system call, before making the function call. And once we return back from the function call, the data is moved back from memory into the R2, right? So in this case, in this way, we are sure like even our if Kali was overwriting these registers, any of these registers, we still have their correct values. After this, after doing this, these steps, if now we will do the computation, we will find the correct result of 3, because even if it R2 was overwritten here, after we return back, we get the old value from the memory and put it in the R2 and then add it. And when you add it, you will get the 3. Okay. So if any questions, please let me know. Okay. Uh, so, uh, so these R2 to R17, it is the responsibility of the caller to save them and restore them. And okay, I will come back. I want to go in the sequence like from R0 to R1, then R2 to R17, and then R18 to R27. It is the responsibility of the caller to save them and restore them, right? So what does it mean? It means exactly the opposite of what we said earlier for the R2 to R17. So if I go back to this example again, So let's say that in this Kali function, here I am going to use register 18, right? But I am not sure whether the caller, which is the main, was actually using R18 or not before making the function call to me. So then I don't know. So it's my responsibility that I save this R18 in the memory, whatever its solder value is. Let's say its solder value is, I'm just making up some number, 10. So I put it in memory. I put a 10 here, and then I use it, use the register R18. For example, let's say I want to now put 100 in R18. And once I'm done with my computation, so before returning, I must like reload these registers, restore these registers. So which basically mean that I should put 10 back in the R8, R18 register from memory. Okay, so in this way, I am sure like even if the caller was using this register, I am safe because I am putting the older value in memory before overwriting it, and once I'm done, I am restoring it from the memory. Okay. So So it is the job of the Kali to take care of these registers R18 to R27. And then we have some registers R27 to R26 and R31 to R30 and R29 to R28. So these registers are used in pair, and they are uh, used to create pointer registers. What do you mean? What do you mean by pointer registers? What is a pointer first? Pointer is basically an address in memory, right? So if we want to store an address in the memory, or for example, if we want to access an index array, it's a little bit. Let me try to explain. So for example, let's say you have an array of data. Again, one note. So sorry. So let's say you have this data available here, right? And I'm naming this as array A, and it has elements indexed as address 0, 1, 2, 3, 4. So I know that I have the start address of the array, which is the same as the address of the first element, right? Which I'm naming as base address. I'm just writing BA for that base address, right? So I can access all other elements by adding displacement or offset in the base address. So let's say if base address of the first element is, let's say, I don't know, maybe X, and then the size of each element is, let's say, 1, then the second element I can access it by using X plus 1, the second one, next one at X plus 2, and so on, right? So for that, I can use the registers in a pair or in a combination, right? And there are like three combinations which are available. One is like R27 and R26, R31 to 30, R29 and R28, right? So these are collectively known as pointer registers. So X is actually, it is known as pointer register, but it is not actually a real register. It is just a name for the combination of R27 and R20, R26 and R27. Okay. Okay. So these were the conventions. So what does it means? It means that you should actually avoid using R26, R27, actually R26 to R29 for holding your temporary values. You can, but it is like, it is a convention or a practice that you should typically avoid using them for holding your data, other than when you are accessing arrays, right? Or when you want to use them as pointers. So somewhere we will see examples of how they can be used. Okay, so okay, so now let's say we are yeah, that's the problem when you prepare the slides like 2 weeks before, and then they get like out of your memory, and you are not 100% sure what the slide is doing. So anyway, let me have a quick look over this, what we are doing. Yeah, okay. So it is basically we are just here seeing that how the program is executed. We remember we had a similar simulation or animation earlier, where we saw that how program counter it iterates through all the instructions in the instruction memory one by one, and then they are executed. So here we have initially program counter set to 0, which basically means that it is pointing to the uh, first instruction. Let's say that this is your program which you want to execute. So when you like this written in assembly, when you will convert into the machine code, it will look like this. So for every instruction, you will have a machine code, or definitely will be represented as combination of bits. And on the first column is showing the location in memory, like memory addresses 0, 0, 1, and so on, right? So we start with the program counter equal to 0, which means that we first execute the first instruction. So it is fetched in, and then the instruction is decoded. And then in the same way we continue with all the instructions one by one. uh, yeah, until you reach to your last instruction. So here what we are seeing is that all the instructions are executed in a sequence, right? So if we want to have a look that in the detail that like how the instructions are fetched and executed in what sequence, so we can use this figure on the left side, which was actually the design of the old architectures, where what happened is that instructions are fetched and executed in sequence. So it basically means that first instruction is first fetched in your processor, and then it is like decoded, and then actually there are more stages. It is not only fetch and execute. It is like fetch, decode, execute, write back, commit. But here we are keeping the things very simple. So we are saying it takes only two stages to complete the execution of an instruction. So in old architecture, what was happening that when you have only one instruction in the processor, within a processor at a given time, right? So once you are done with the instruction one completely, then you bring in or fetch the next instruction, instruction two. So it also moves through the stage, like from fetch stage to the execute stage. And once it goes out the CPU, then you have the next instruction entering the CPU. And in this, your program gets executed in this fashion, right? But this is like not good. Why this is not good? Because it is it is slower in terms of the performance, or it takes longer for each instruction to execute. Why? Because if I go a little bit back, so here when I'm saying that my instruction 2 is in execute stage, my fetch stage is empty, right? So I am like wasting the resources. So what I can do is that I can use the pipeline approach. So in the pipeline approach, which is shown in the next slide, what we do is that we keep our all the stages occupy at all the time. But then again, one instruction can occupy only one stage at a given time, which means that we fill the other stages with different instructions. So let's say we have instruction one entering the CPU, but when it moves from fetch to execute stage, we bring in the second instruction and put it in the fetch stage. And when that instruction one moves out, instruction two goes to the execute stage, and instruction three enters the fetch stage, and so on. So what happens now that our it takes less time for our program to complete its execution, right? Any question here? So that was like one thing how you can speed up basically your execution of your program, like by using the pipe. There are also other mechanisms, but this is a one approach, right? So how can we speed up the CPU other than pipelining? Definitely one straightforward way is that you can increase the clock frequency, because clock frequency normally what happens is that your one instruction is executed every clock. Let's say in ideal cases, right? For example, most of the instructions in your AVR microcontroller, they are executed in a single clock. So if they are executed in a single clock, if you make the clock frequency higher, it's mean uh, you can execute more instructions in the same amount of time. Again, let me go back to uh, OneNote. Okay, so uh, suppose that we I have this Suppose that I have time on horizontal axis. So this is time, right? And let's say this is my clock signal. So this is, let's say, logic 1 and this is logic 0. Okay. And this is my clock signal here, right? So if I'm saying that my one instruction takes one clock cycle, so how many instructions I can complete in this time period? I can complete one instruction here, and then I can complete another instruction here, right? So in total, I can execute two instructions. Now, if I increase the frequency, it's mean that my clock is switching between 1 and 0 more frequently, right? So if it is switching more frequently, let me again draw the clock with double frequency as compared in the first figure. So here actually I'm doubling the frequency of the clock. And again, if I'm saying now again my one instruction takes only one clock cycle, so I can execute one instruction here, the second one here, third one here, and the fourth one here, right? So now I can execute four instructions in same amount of time. The amount of time which is spent is actually same, right? But the clock frequency is increased, right? So now four clocks are happening in the same amount of time as compared to the first situation, which means now I can complete four instructions. So I am like doubling my performance. So I can complete my program execution in half of the same time, what I was doing earlier. However, there is downside of that. One thing is like if you increase the frequency, then you incur more power consumption, and which basically means that your hardware becomes heated quickly, uh, and then you need some mechanism to like to cool it down. Not only that, if you are using microcontroller, which is mostly used in embedded systems, they and like you have very high frequency to you are increasing the high frequency to speed up the execution or speed up the execution of your program. So it's mean you are consuming more power, but in embedded systems most of the time you are already limited on the power source, right? So you want to be like very efficient when consuming that power. Other thing is like you cannot increase the frequency for like to infinity, because then you end up having the hardware limits, or which basically means the physical limits for the transistors, because all your devices are made up of transistors. But when you continue reducing their size, then eventually you reach a point where you cannot increase the reduce the size of the transistors beyond that point because of the physics limitations imposed by the physics of the devices, right? The other thing is like you can instead of like clock only increasing the clock frequency, you can also change the architecture, or you can make the architectural changes. And one example of that is what we have seen already in the previous slide, like at a very simple level, pipelining, right? The other is like you can use the risk approach. So what is risk approach? uh, uh, let me explain. uh, or maybe I can first go to the slide, go over through the slides, and then I can explain, because I wanted to draw a figure to explain why how risk can help in improving the uh, speed of the CPU, right? But let's first talk about risk, and then I will try to explain how it can help in speeding up your CPU. So risk basically stands for reduced instruction set computer, and the alternative to it is complex instruction set computer, right? So complex instruction sets computer, it supports as many instructions as possible. On the other hand, risk, it supports fewer number of instructions. And then programmers, they use those fewer number of instructions to complete complex tasks. Let me see if there is an example or not. There is no example. Let me explain then. So what we mean by having as many instructions as possible, and what we mean by when we say that risk can use the fewer number of instructions to complete the task. So let's say that let's say that you have a CISC processor, right? I'm just giving an example. Let's say you have a CISC processor and you want to implement the multiply operation, right? So it will give you a multiply instruction. It will provide you a multiply instruction or mul instruction, right? This is just a simple example. So providing the multiply instruction basically means that you have the hardware support available for executing the multiply instruction, which means that in your CPU you have a hardware component which is responsible for multiplying two input numbers, let's say A and B, and then provide the result, let's say product, right? But designing multiplexers, so what is the advantage of implementing the multiply instruction in hardware? The advantage is that your execution will become faster, because anything there are, whenever you are doing some computation, you can either do it in software or you can actually implement the hardware component to do that. When you do it in hardware, it is always faster, right? So why? I don't want to explain it at this point. Why implementing in hardware is faster? Because you are actually uh, just transmitting the electrical signals, and transistors are communicating with each other to implement the task, right? So it is always faster. Now in sys processor, let's say we have multiply operation, right? So it means that user don't need to do anything extra. If you want to multiply two numbers, let's say you only say multiply A and B, so then your result will be available in A, right? On the other hand, in risk, what we do is that the philosophy of risk is to have as much less number of instructions as possible, but still able to do the same task which sys can do, right? For example, the task we are doing here is multiply operation. Now let's say talk about risk. In risk, let's say we don't have multiply operation, multiply instruction, but we have, it is so difficult, okay, so but we have add, right? So if I want to do A and 8 multiply B, it means what? It means I am adding B A times, right? So let me give you a concrete example, 2 times 3, right? So I'm just saying, okay, I'm adding 3 two times. So I'm basically doing add operation. Or if I want to say 4 times 3, so I'm adding 3 4 times, right? So I can use add, I can use, okay, add. For example, in our AVR microcontroller, I can put R0 in, I can put, let's say, 3 in R16 and another 3 in R17, and then I can say add R16, R17. So it will give me 3 plus 3. Then I will say again add R16 to R17. So it will give me 3 plus 3 plus 3 and another last one. So it will give me addition of 3 4 times, which basically mean is 4 times 3, right? So I'm able to multiply the both numbers by using the add, right? But I don't have multiplier in my machine or in my hardware. I have only adder, right? Now I'm, let's say, here giving A, B, and here I'm adder. Now the thing is that designing adder in terms of hardware cost is less cheaper as compared to designing multiplier. So you are like avoiding the hardware complexity in risk approach. You can still do the same thing, but now the thing is like you are, if we assume that each instruction take one cycle, so now for multiplying 4 times 3, you are using 3 cycles, 1, 2, 3. But here you are using only one cycle. So it is faster, but it is like complex in the sense that it provides support for so many instructions, right? So your hardware becomes more complex. And here we gave only an example of like multiply operation, but this is like just one example. There are other cases where situation becomes even more complex, right? So this is what we mean by risk and risk. Any questions at this point? Okay, so now I think this statement will make sense to you. So why we name CISC as complex instruction set computer, because it supports as many instructions as possible. And when we mean support, it's mean that those instructions are actually implemented in hardware. There is underlying hardware which supports the execution of those instructions, as compared to the risk, where we have reduced instruction set computer which support fewer number of instructions, right? and then programmer can use those instructions in combination to complete complex tasks, just like I gave you an example of doing multiplication using repeated adds. Okay, so let's have a look at features of a RISC architecture. The first thing is that the RISC instructions are fixed in size. In RISC computers or RISC architectures, for example, our AVR microcontroller, it is a RISC architecture, and the advantage of having how to say having fixed size instructions is that it simplifies the instruction decoding. For example, our let me again use the pointer. So for example, in AVR microcontroller, we have most of the instructions are 16-bit in size, or 2 bytes in size. There are few instructions which are 4 byte, but most of them are 2. Most of them are 2. So when you have for all the instructions, or let's say for majority of the instruction, the size is 16-bit, right? So let me try to give you an example how it makes easy for to decode the instructions. Because first thing is like if you have this instruction which is 16-bit in size, starting from bit 0 to bit 16, right? Then first thing is that you always need to this data actually is read and it goes to the your decoder component, right? So there is, since there is no variation in size for most of the instructions, or let's say for all of the instructions, so decoder knows that I only need to read the 16 bits, right? And as compared to this, if we have a situation where our, let's say, 10% of instructions are one byte in size, having 0 to 7 bits, and then other 25% are 2 bytes, and another 25% is 4 bytes, and the next is like, let's say I'm making simply an example of 8 bytes. So then decoder will be right in all the cases. You don't know which instruction you are, the next instruction whether which you read, whether it will be 8 byte, 1 byte, or 2 byte, or 4 or 8. so so you will need to read all, like you will have to read all the 16 no, sorry, if it is 8 byte, 8 times 64, you will have to read all the 64 bytes. And then when you look at the opcode of that instruction, you find out, oh, I am reading 64 bytes, but actually this instruction is only 1 byte, so I need to discard other thing, and I don't care about them, right? So your decoder will become more complex. Because when you have variation, so you need to take care of, in variation in your design, you need to take care of all different possibilities. Okay, so for example, okay, so what about CISC? In CISC, instructions are variable in size. So for example, in 8051, which is not a RISC processor, it is actually a microcontroller, but it is not based on RISC design. It is based on CISC. So it has instruction clear C, which is 1 byte in size. Add instruction is 2 byte in size, and long jump is 3 byte in size. But in your AVR microcontroller, we have either 2 or 4, but majority of the instruction, like I guess there are only 3 or 4 instructions which are 4 byte in size in AVR microcontroller, and all other are 2 bytes in size. Okay, so we have already talked about this feature that RISC has fewer number of instructions, which basically mean that when you are designing this type of architecture, you need fewer transistors. Uh, but then assembly programming becomes more difficult. Why? Just like have shown you, like in to do the multiplication 4 times 3, you need to write 3 add instructions to do the same thing, which you can do using single instruction in CISC. And it also takes more memory. Why it takes more memory? Because your program size becomes longer or bigger. So if your program size is bigger, then it takes more memory to save your program, right? Uh, Another feature is that you have limited addressing modes in the RISC. Uh, what is what is an addressing mode in the first place? So the addressing mode is basically like how you can specify the address of a memory location which you want to access in an instruction, right? So for example, one way is like you can directly put the address in a register. Let's say I'm just making up any register, and then you say, okay, read data from this address. Another way is like, okay, you are putting the address in two registers, R1 and R2. Actually, it is not plus sign here, but let's say comma, R1 and R2. And then you are saying use this one as base address and use this as index address, right? So these are like so these are different addressing mode, right? So here you are providing the base, and then you are adding some index to the base address, and like in different iteration of your program, you can increment the index. Just like if you consider that example of uh, iterating our elements of an array, which I gave you earlier, right? So the addressing mode basically mean how you are specifying the memory location, address of the memory location which you want to access, right? So if you have limited addressing modes, this means your hardware will be less complex. But if there are like let's say 7 different ways of specifying the location, it will give you more flexibility, but it will make your hardware more complex. Okay, so risk architecture, again, our AVR is risk architecture. It is a load store architecture. What is meaning of load store architecture? Load store architecture basically means that I will explain this example on the left, but let me first tell you what is load store architecture. Load store architecture is the is a design where data can be data can be brought from the CPU, sorry, from the memory into the CPU only through the load instruction, and then you can operate on the data. Like for example, if you want to do add operation between two numbers, and one number is in a register and the other number is located in memory, you cannot do the addition. You first must read that data or load that data from memory into a register and then add the two registers together. Similarly, if you want to write some data in the memory, so first the data you want to write must be loaded in the register. You cannot directly write an immediate number into the memory, right? So here is an example. So we are saying, okay, load the data from memory address 0x200 into R20, and then load another data from a different address 220 into R21 register, then add them together and then put the result back in the memory at address 0x230, right? So here what we are doing addition on two registers. We are not doing addition between a register and another operand which is located in memory, right? So this is known as load store. You can only access the data once it has been loaded from the memory into the registers, right? So again, this keeps the design simple, but then it keeps but it makes your program slower. So for example, compare it with the situation where you have an architecture which supports adding two numbers. Uh, let's say it supports adding two numbers. Okay, let me go back. I was like trying to be lazy. I didn't want to go back to one note, but then it's very difficult to write on the slides. So, for example, let's say you have a processor or a microcontroller which allows you to add two numbers together, which are located in the memory. So, for example, you can say, okay, add 0x200 and 0x 220, so which basically mean that read the data from this memory address. A is located here, let's say, and read the second operand B, which is located in memory at this address, add them together and put the result back in this location, right? So what are you doing? You are completing that same thing in one single instruction. If you compare it with the example given in the slide where we are doing 4 different instructions, right? So the program is faster, but your hardware will become more complex. Why it will become more complex? Because now you are saying that you need to be able to load the data directly from memory into the ALU. What we are doing in AVR, we are first AVR microcontroller and risk architecture. We are first loading data from memory into the registers, and then from registers to into the ALU. But if you want to read data directly from memory into the ALU, your design will become more complex. And not necessarily it will be faster, because you will be accessing memory. Again, it depends where is your memory located. It is located on chip or off chip, right? But let's assume if we even say if it is on chip, still your design will become more complex. Okay, so the other thing is that your AVR microcontroller is using the Harvard architecture, which basically mean it has separate buses for both opcodes and operands. Opcodes basically mean code and operands mean data, right? So the advantage is that you can opcodes and the operands, they can go in and out of the CPU together because they have separate buses. We have already discussed it earlier. But the disadvantage is that it leads to more cost in general purpose computers. If you implement it in, like, not in microcontrollers, but in this approach, but in general purpose computer, so you will have a separate chip from core memory, separate chip for data memory, and there will then the buses which will be which will be crossing the chip boundary, because CPU is another chip, right? So the communication will become much more expensive. Okay, so let's say this is our example. Uh, Again, since I prepared, I had these slides like 2 weeks ago. Now I don't remember what this example is telling us. Let me quickly have a look at it. Okay. Yeah, okay. So we are first fetching the first instruction, which is actually loading the data from a memory address into the register R20. And then we are fetching the second instruction while the first instruction goes into the execute stage. In the second instruction, we are adding these two numbers together. And then we are done with our program, right? So how it becomes possible that we can do that? Because we have the pipelining available in our design. Okay. In RISC architecture, another feature is that more than 95% of instructions are executed in one machine cycle, because unlike RISC architecture does not imply micro ops. So uh, what are micro ops? Micro ops basically stands for basically is like breaking down a complex operation into smaller atomic operations. So in CISC, what we do is that we break a complex instruction down into smaller atomic operation and name them as micro ops. And why we do that? So that because the complex instructions are hard to decode quickly and it is difficult to perform them in parallel. Basically, it means that it is difficult to perform them in pipeline fashion. And unlike those complex instructions, micro-ops are most suitable for pipelining because there is less variation relatively in their execution time. We will see an example, and then you will understand what we mean by macro-ops and what we mean by breaking a complex instruction into micro-ops. Also, not all instructions in the CISC architecture need to be broken down into micro-ops, because some of the instructions, they are already in the atomic form. They cannot be broken down further. So here is an example. Let's say we have increment EAX, and let's say we are talking about CISC processors. So this has an instruction increment EAX. So it is already in atomic form. We cannot break it down further. So we are simply saying that add the value of 1 into the EAX register of the processor. But let's say now we have a look at another example of an instruction where we are saying like add the value of EAX register to the memory location at a given to the memory location whose address is given. In this case, mem is the address, right? So we can break down this complex instruction into three micro ops. We can first say, okay, first load the data, because here what we are doing in this instruction, we are actually doing three things. In this instruction, we first have to do three things. What are those things? First, we need to read the data from memory, right? And then add that data with the value of the EX register. And after doing the addition, we need to write the result back in memory. So if we do all these three functions or operation as a single instruction, it is difficult to pipeline the functionality of the add of this add instruction. So what we can do is that we can break it into three micro ops. In first micro op, we say only load the data from the memory into a register, let's say some temporary register. Then add the EAX register with the value of the temp register and put the result back in the temp register, and then put the value of the temp register in the memory, right? So here we are saying load, here we are saying do the operation of add, and here we are saying do the store operation. So since we have now broken it down into three micro ops, so when our first micro op is, let's say, in execute stage, we can have second micro op add in the fetch stage, and when our add operation is in execute stage, we can have store operation in the fetch stage, right? And also, since these micro ops, they like most of them take much less time as compared to a complex instruction, we can complete them quicker. Any questions? Okay. RISC processors, they have at least 32 registers. I don't think this is universally a true statement, but they have sufficient amount of general purpose registers, which reduces the need for stack and memory usages. So for example, in AVR microcontroller, we have 32 general purpose registers, so we can hold our temporary data in those registers, and we don't need to go and write our data in the memory. Compare it with the case where you have smaller number of the registers, so then you will have to like frequently put your value into the memory because you don't have any more registers available. Any questions? No? Okay. Before we go to the next topic, let me uh, yeah. There were two questions last time which I were not able to maybe answer with complete certainty. So one was like, remember we were writing, let me open the slides, then I can show you. Yeah. One was this question, like when we are writing our code in Arduino IDE and here we write extend C. So what is the meaning of C, right? When we are defining a function in our assembly with the name of compute in the Arduino, when we in the main file, in the .ini file, before after extend we put the C. So what is the meaning of the C? And I said like most probably we are telling the assembler that this code is written in C. So this was correct understanding, but there is a bit more detail which I want to discuss. So the thing is that Arduino, it actually compiles your code as C++ code. If you by default, it compiles your code as C++. Now in the C++, the thing is like you can overload the functions. Like you can have same function, but they can have different meaning at different times depending upon what parameters you are providing to those functions, right? But we don't want to do that. We don't want to have the function overloading when we are writing the assembly code, right? So that's why we say that, okay, compile this function, this treat this as a C function, not as a C++. Why? Because in C we don't have function overloading. So that's why we are saying, okay, use consider this function as a C code. So that was one question, and there was another question which was uh, yeah, which was about uh, uh, carry flag and overflow flag in the status register. I think I can keep it for the time when we come back again to the status register, and then I can discuss it there. Or if I forget, you can remind me. Okay, so with this we are done with the second module of the lectures, which was about internal organization or architecture of the AVR microcontroller. and at a like relatively at a simpler level, at a higher level as compared to the detailed study of the architecture. uh, and now we are moving to the next module, which is about branching and arithmetic instructions. We have already started using them in labs, but we have not discussed specifically the branching instructions in detail in our lectures. So this is what we are going to do in this set of slides. So we will cover compare instruction and branching instructions. We will have a look at some more addition and subtraction instructions. We will also discuss carry and overflow. Yeah, the second question was carry and overflow flag, so I can answer that question or address it at that point. And then we will also talk about logical instruction and masking, but not today. So the last three bullets I will try to cover them in the next lecture. And today is Thursday, right? So you also have a quiz. Okay. So comparison of numbers. So when we remember when we were talking about status register, we discussed about some we covered several flags like carry flag, Z flag or zero flag, negative flag, overflow flag, sign flag, and half carry flag, right? So when you are doing the comparison of numbers, in that comparison, the we actually use we base our comparison by looking at the value of these two flags, C carry flag and Z flag. But here we are talking about unsigned numbers. So when you are comparing unsigned numbers, actually your microcontroller hardware will be looking at the value of the C flag and the zero flag, right? However, these two flags are not sufficient when you are comparing the signed numbers in your assembly language program. And for that, when you want to compare the signed numbers, the microcontroller will use other flags as well in addition to zero flag. And those flags are your negative flag, overflow flag, and sign flag, right? So is everyone clear about C flag and Z flag? Carry flag and zero flag, how it works, right? We had several example last time. Anyone who doesn't understand how these two flags work? Everyone is clear, right? Okay, now let's have a look at, and also I gave you an example, right, in the description of the lab, like how C flag is used in comparing the numbers, right? Like how the value of C flag, like if it is zero or if it is one, what does it tell us, right? So let me give that example quickly again. Yeah. Again, I am going to use 4-bit numbers to keep our example simple and so that it takes less time. So, uh, I'm not covering the zero flag because that is simple. If the result of an operation is zero, then our Z flag will be equal to one. If the result of the operation is not zero, then Z flag will be equal to zero. Okay, so I'm not going to cover it in the example. But for the carry flag, let's say I have this number 0, 1, 1 and 1, 0, 0, 0. So if I'm adding these numbers, so I will get the result 1, 1, 1, right? So I am assuming I have 4-bit register, so there is no carry out. So my C flag will be 0, which basically is telling me what. Okay, now in place of addition, let's say I want to do subtraction, right? Let's say I'm using the compare instruction. Let's say I'm comparing the numbers. I'm not writing register values. I'm directly writing the values itself, not register names. So let's say I want to compare 3 and 2. So if you have read the description of the lab, so what does the compare instruction do? It subtracts the source operand from the destination operand, but it doesn't write the result back in the destination register. So basically what we are doing is we are saying that it will do 3 minus 2, right? So if I convert into the binary, so into 4-bit binary, 0, 1, 1 and 0, 0, 1, 0. Now if I do the subtraction, so 1, 0, 0, 0, right? So there is no carry in the most significant bit. So C is equal to 0. So what is the information conveyed by this flag? So this flag is now telling me that first operand, let's say I'm naming is RD and this is RR. So it is telling me that destination register is either same or greater than the source register. So here we have greater, right? So 3 is greater than 2. So then C flag is equal to 0. We can also have another example where we have the same values. Let's say I do 2 minus 2. 0, 1, 0, 0, 0, 1, 0. When I do the subtraction, I have 0, 0. Sorry. Yeah, 0, 0, 0, 0. There is no carry in, right? Or borrow in basically. So C is still 0, right? So when C is equal to 0, then we are saying that, okay, now the information conveyed is that uh, the first number is either same or greater than the second number, the source, right? Now, if I simply change the values, let's say I have CP compare 2 and 3. So this is destination now, and this is source. So 2, I am doing 2 minus 3. So which is basically 0, 0, 1, 0, 0, 0, 1, 1, right? So I take a borrow here. So 2 minus 1, 1. And here I'm left with 0. So I take a borrow here. But then from here, this location. But it is 0. I need to borrow from here. But it is 0. So I borrow from the next one, right? So there is borrow in the most actually less than the sorry, destination register is less than the source register. So this is how carry flag is conveying me the information, and this is how we can use the carry flag in comparing the signed number unsigned numbers. However, carry flag is not enough when only carry flag is not enough when we are comparing the signed numbers. We need to also use the other flags. So what are those flags? Like negative flag, uh, overflow flag, sign flag, and Z flag, right? So remember that when we are comparing the unsigned numbers, we are not converting for here. For example, here when I was doing 2 minus 3, I was not converting 3 minus 3 to its 2's complement form, right? Because I'm treating the numbers as unsigned numbers. However, if I treat them as signed numbers, so I need to then first convert 3 minus 3 to its 2's complement form, which will be, so minus 3 will be, first I need the binary of 3, then I do 1's complement, then I add 1 to it, so it becomes 1 0 1 1. So this will be 2's complement. Now if I'm using the signed number representation, then carry flag will not give me the information about whether the source is greater than or source is same or greater than or less than the sorry, destination is greater than, same, or less than the source operand. For that, I need to look at the uh, I need to look at the negative flag. So if the negative flag is 1, then it's mean that the result is negative. If the which basically mean that the first operand is source is smaller than the second one, and otherwise it is not. Overflow flag. Actually, the thing is that in some situations, your negative flag, even in case of comparing the signed numbers, your negative flag is not enough to give you the correct information. And what are those situations? When your overflow happens. Uh, so in those situations, we need to actually combine a negative and overflow flag and name it as sign flag. So then we look at the sign flag. Okay. So the basic thing which you need to remember here is that when you are using the when you are comparing the signed numbers, C and Z flags will be used by your hardware. But when you are comparing the signed numbers, N, V, S, and Z flags will be used. Again, you can ask the question, okay, how can our hardware know whether we are comparing the signed numbers or unsigned numbers? Because numbers are numbers. Are we going to specify that whether this number is signed or unsigned? Actually, no. Uh, then how does the hardware know whether we are comparing unsigned or signed numbers? So it knows by the type of the instruction we are using, because there are different instructions for comparing the signed numbers, and then a different set of instructions for comparing the unsigned instructions. So we have a couple of minutes. Let me cover this slide. Branch instruction. So branch instruction is used for comparing unsigned numbers. Okay, so basically, which means that it will be using it will be looking at the carry flag. So what is the syntax? The syntax is like you simply put the name of the instruction, and after that the address to which you want to branch if your condition is true. So this instruction actually says branch equal. Branch equal mean what? If your two numbers which you are comparing, they are equal in value, then go to this label. Okay. And this is the opcode of your, this is the format of your instruction. So these bits together, they make the opcode, right? And these remaining bits, they make your 7-bit address, 7-bit address of the instruction where you want to go if the two numbers which you are comparing, they are equal in their value. So your operand, which is basically an address in this case, is a 7-bit value, and it is in it is a two's complement number. So if it is 7-bit and is represented as a two's complement number, then its range will be what? From -64 to 63. Okay. I don't want to go again to discuss how this range is calculated. Remember, we discussed it in like first or second lecture, I guess, or third lecture. How we can calculate the range of a two's complement number, which is, let's say, n bit in size. So this instruction cannot read instruction too far away. So for example, if you are saying branch, okay, let me stop here because we are in 2 minutes. We have only 2 minutes, and I don't want to rush over this slide. Otherwise, you will not able to understand it. So next lecture we can start again from the same point. And yeah, now you can go ahead and take your quiz. And I am here available until the end of the lecture time. Okay, but I'm stopping the recording.